Hello there and welcome to the course Probability Methods in Civil Engineering. Today we are starting a new module, module 3. In this module we will learn about random variables, and there will be a couple of lectures, and in this first lecture we will learn the concept of random variables and their definitions. So, our outline for today's lecture is arranged broadly like this. First we will discuss about concept of random variable, and then we will understand the definition of random variable. Then we will discuss different types of random variables and their probability distributions. These random variables are important in the sense that this concept is important to understand how it is used in the probability theory, and this probability theory for this random variable is generally generally assessed through their distribution. So, it is known as the probability distribution of random variables, and after that we will learn different properties of random variables. So, as just what we were telling, that this concept of this random variable, which is abbreviated as RV, is most important to the probability theory and its application. Now, if we see that what actually this random variable mean, if this shaded area what you see here is a sample space, then this sample space consists of all feasible outcome of one experiment. Now, this feasible outcome of this experiment can be continuous or can be discrete points from through this sample space. Now, from this sample space we have to, for the mathematical analysis, we have to map the outcome of the experiment of one experiment to some number according to our convenience. Now, to map this each and every output of a random experiment to this real line is generally through a functional correspondence, and this functional correspondence is one random variable. So, what is important and what we want to understand from this slide is that this random variable, even though this variable is shown here in the name of the random variable, is not a variable. So, which is generally what we want to say is a functional correspondence, or is a function. That function generally map between the sample space of one experiment to the real line. Now, this mapping is done based on our convenience, and that we will see in a minute. Thus, if we say the definition is, if we say, then we will see that a random variable is a function denoted by x or x some specific number. It can be denoted by any letter. Generally, these things are denoted by the small lower case of this random variable. These random variables are generally expressed in terms of the uppercase letters. So, this random variable x is a function that map each points, that is the outcome of an experiment, over a sample space to a numerical value on the real line, what just we shown in this figure in the last slide. Now, before we discuss some of the further concept of this random variable, so there are different notations are being used to denote this random variable and the specific value. For this lecture, or you will see in some of the classical textbook, that this notation will be followed for this course. Generally, this random variable are denoted by the uppercase letters, and its specific values are denoted as lowercase letters. Thus, in this notation, this uppercase letter is indicating the random variable, which is denoted by this x, and any specific value to this random variable is denoted by this small x, which is shown here. So, this is the specific value of the random variable x. Now, we will see some example of this random variable which we just discussed. Suppose that number of rainy days in a month. So if we can say that this is a random variable and we don't know, so this value, the number of rainy days in a month can vary, and if we denote this random variable as the letter capital D and some value, say D equals to 5, so this indicates that 5 rainy days are observed in a particular month. Now which can be expressed by D in parenthesis D equals to 5. Second example, say the number of road accident over a particular stretch of the road in a year. Suppose this is denoted by x and some specific value such as say x equals to 10 indicates that there are 10 road accidents over that stretch of the road has occurred in a particular year. Now this value 10 or this value 5 can change in the successive time step, or in the in this case in the successive year, that can change. So this number of road accidents is my random variable, which for a particular year it takes a specific value x equals to 10, which is denoted by this. The last one, say the strength of concrete, if I designate is at C, so this is denoted by C, and some specific value such as C equals to 25 Newton per millimeter square indicates that 25 Newton per millimeter square strength was observed for a particular sample of concrete, and which is expressed by C in parenthesis C equals to 5. This will be C equals to 25. Sorry for this mistake. This would be 25. So a little bit formal definition of random variable. If we see that a random variable x is a process to assign a number which is a real number x xi to every outcome xi of a random experiment. So if we just take that thing, so suppose that we are taking that example of tossing a die, then we know that whatever the numbers that generally comes, if it comes a 6 on the top, then we say that the outcome that is coming, it is my 6. Similarly, 6 different surfaces can have 6 different numbers, and that can be happen. Now see that in this experiment, if I just change this one, so this is quite straightforward. The whatever the number of dots that we are usually used to know. Suppose that instead of having this kind of dice, if I just have a dice which is having different colors, suppose that this is having a blue color, this side is having my say red color, this side is having green color, and similarly 6 different face is having 6 different colors, then what I am trying to do is that this outcome of this, the top surface, the color of the top surface, if I just want to say that this is my outcome of this experiment, then what I can do is that I can take different color code and I can assign to some number, not necessarily 1 to 6, it can be of any number. Say that B, I am giving some number 10, R giving some number 20, green giving some number 30, and in this way say up to 60 this number is given. So this mapping from this outcome to some number, this mapping is your random variable. So we will come after this how to assign the probabilities. Now this is very straightforward. So each and every outcome, if this dice is fair, then the outcome of each and every of this outcome will be equal. So everything will be 1 by 6. So that is again another process how we will assign the probability to that particular random variable if it is x. So that will be how we assign the probability. Now when we are defining this random variable itself, so this random variable is nothing but is a process to assign a number to each outcome of that random experiment. This is exactly what we are calling it as a formal definition of this random variable, is that a random variable x is a process to assign a number xi to every outcome xi of a random experiment. The resulting function must satisfy the following two conditions. So, even though we are saying that this is a function, so this function of mapping from this outcome experimental outcome to some number should follow to such two conditions. The first condition is that the set x less than equal to small x. Now, you see here, this is a capital letter which is your random variable and this is the specific value. Now, this random variable below some specific value is an event for every x. So, whatever the x you take, so this should constitute an event for that random variable, for that for this x. Now, other things are probabilities of the events that x equals to plus infinity and x equals to minus infinity are equal to 0. Why these things we are just saying is that even though means mathematically this x can take any value on the real line, but still we say that, so the extreme, that is the plus infinity and minus infinity, these probabilities, if I take this probability, this would be equals to 0. A complex random variable. So, just we will call to complete this definition part. If we do not say this one, it will not be completed. So, this is, there is another type, this is the real random variable which just we discussed. Yes, now it can be the complex random variable as well, which is say z equals to x plus I j I y. So, this random variable is only defined by their joint distribution. So, if I want to define the complex random variable z, this should be defined by their joint distribution. This joint distribution will be discussed later in this course. So, but for the timing, you can say that this joint distribution is generally obtained from the distribution of this x and y both. So, both these distribution should be taken care to find the joint distribution to define the distribution of the complex random variable of the random variable of individual x and y. Since this inequality, because so this kind of inequality, say these are the random variable and this is the less than equal to that number, does not exist. But for this course, if it is not stated specifically, all the random variables are real. We should follow this norm. Now, with this concept, we will just see different types of random variables. There are basically two types of random variables. One is the discrete random variable and other one is continuous random variable. But there are sometimes, in particularly in the civil engineering application, we have seen there are some distribution which can be treated as the mixed random variable as well. So, we will discuss these different types of random variable one after another now. The first, we take this discrete random variable. If the possible set of values that a random variable can define is finite, it is a discrete random variable. Now, so just to tell this thing here, that suppose that this is my sample space. Now, if I say that this random variable is defined for some specific values and rest of the part it is not defined. So, it takes some specific values. So, those values only it can define. So, in that case, what we say that this is a discrete case. So, in the previous example, if we just see here, that it can define that some specific outcome of this random, it is not that continuous, that a range cannot be defined here. So, if it is dots, then we can say that it is defined for the outcome 1, defined for the outcome 2, but it is not defined for the outcome any number in between these two. Similarly, if we just see from this remote sensing concept the color code, then we can say that it is defined for the blue, for this colored surface it is defined for the blue, it is defined for the red, but in between mixture, I think you know this color code. this stands for this blue if it is the color RGB are the primary colors, and this 100 is for the red. Now you can just change this number to some extent to get some in between color, so that is not defined there. So what we want to say for this discrete is that these random variables are described only for some specific outcome of this experiment. It is not defined for this all. So those random variables whose outcome, who can define the outcome of the random experiment for some specific values, those are known as the discrete random variable. Thus, if the possible set of values that a random variable can define is finite, it is discrete random variable. The probabilities are defined for the specific values which are greater than or equal to 0. So this we will see in details, which are greater than and equal to 0. But what we are trying to stress here is that the probabilities are defined for the specific values. So it's just like that for that point these probabilities are defined, for the adjoining point this is not defined. Summation of all the probabilities, all the possible values are equals to 1. These two things are basically coming from the axioms of the probability theory that we discussed in the previous classes. The next type is continuous random variable. So on the other hand, in contrast to this discrete random variable, if the possible set of the values that a random variable can define is infinite, it is continuous random variable. So over a zone, over a range, this random variable is, if it is also defined, then this is known as the continuous random variable. The probability of any specific value is 0. Now this is coming from this density point of view. Now once we are saying that this probability of any specific value, if I just take, then this specific value probability is 0. This is again coming from the axioms of this probability. But even though we say that it is exactly specific value, it is 0, but whatever small set of the values, if we think, that can be greater than or equal to 0. So whatever the small range, if we consider, then it will be 0. I think this will be more clear from this pictorial view here. So suppose that what we are trying to say, that if there are some specific outcome and those probabilities are assigned like this, whatever may be the probabilities, if it is not equiprobable, so these are like the concentrated mass for that specific outcome. So this is your discrete random variable. Now for this continuous random variable, what is defined is that it looks like this. So over this zone, from this to this zone, for any specific value, this is nothing but the density of this one. Now following the axioms of this probability, if we just add up, this axis is your probability. So if I add up all these values, what we just discussed, this will be equal to 1. But in this case, when we are talking about this is one continuous distribution, then what happens, for a specific point the probability is 0, because this is basically a density. Now whatever the small area that we consider, then this area is giving you the probability for this small zone. Now for the full zone, if I just take, then the total probability, that is the total, this is your feasible range. So the total probability in this feasible range should be equals to 1. That comes from the axioms of this probability theory. Now again here the next type what comes is the mixed distribution. So mixed distribution, sometimes what happens, for some specific value it is defined some probability, probability is concentrated here as a mass, and for the rest of some range it can be continuous and goes up to some level or up to the end of this up to the infinity. So now for this particular point, this probability mass is concentrated here, and for the rest of the region it is having some continuous thing. So in such cases we say that this kind of random variables are mixed random variable. So this is the third thing what we are seen that. So mixed random variable says, if for some range of possible set of the values of a random variable is discrete and for the other range of possible set it is continuous, it is a mixed random variable. So now with these three type of random variables, some example in the civil engineering context we will see now. The first is that we discuss the discrete random variable, say that this number of rainy days. Now number of rainy days at a particular location over a period of 1 month, say, so it can take either the especially the integer values, either 1 day or 2 days, 3 days, in this way up to 30 days or 31 days, whatever may be the case, but it can never take any value in between two integers. So as this can take only some specific values, so this is an example of discrete random variable. Second is the number of road accident over a particular stretch of a national highway during a year. So again these road accidents can be either 1, 2, 3, 4 in this way up to infinity, but it can never take any value in between two integers. So this is also one example of discrete random variable. Third is the traffic volume at a particular location of a road. So this is the number of vehicle that is crossing that particular section of the road. Again this can take only the integer values for that one. So this is also one example of the discrete random variable. Now the example of the continuous random variable, on the other hand, that amount of rain received at a particular place over a period of 1 year. So annual rainfall for that station, for the say that it is a number of rainy days which is a discrete. Now if I just say the total depth of the rain received at that particular point, that can vary from 0 to any possible number. So this is one example of the continuous random variable. Compressive strength of a concrete cube. Now there are different ways, there are different criteria maintaining different design criteria. If we prepare the concrete cube and then we test what is its compressive strength, that can actually take any value between certain range. So this one also one example of the continuous random variable. Now coming to the mixed random variable. So here say the depth of rainfall at a particular rain gauge station. So this depth of rainfall at a particular rain gauge station, which is gave this one, that is as a continuous random variable here. Now if you see that if there are station where most of the days if it is the 0 rainfall for the station, then how it will take. So for a 0, suppose that out of 365 days in a year, suppose that there are 220 days that are 0 rainfall. So there is a probability mass that is concentrated at a particular value of depth of rainfall 0, and for the non-zero value it can have some distribution. So that distribution should have, so the first part at particular value that x equal to 0, that is the depth equal to 0, some mass is concentrated there, some probability mass is concentrated there, and rest of the probabilities are distributed over the positive side of the axis. So this is an example of the mixed random variable. So saying these three types of random variable, it is important to note that another special type of random variable which is known as the indicator random variable. So it is a special kind of random variable associated with the occurrence of an event. So this random variable which says that whether a particular event has occurred or not. Say an indicator random variable IA represents all the outcomes in a set A as 1 and all the outcomes outside A is 0. So it is like that whether yes or no. So if I say that, again if I take the road accident, whether there is a road accident, if there is road accident, these random variables in fixed in such a way, that is that functional correspondence that we are talking about again here. That is, its function is that it will just see whether the accident has taken place or not. If it is yes, then it will say 1. If it is no, it will say 0. So the each day I am just taking this measurement and just preparing that series. So that series consists of either 1 or 0. Again, for the rainy days, I will just see every day whether it is rain or not. I am not interested this random variable if it is designed in such a way that it is not interested what is the depth of the rainfall, only the interested that whether it is a rainy day or not. If it is not a rainy day, then it will return 0. If it is rainy day, it will return 1. So this type of random variable just indicate the occurrence of one particular event. Then in the first case, whether occurrence of the event is the accident, and another one is the occurrence of the rainfall or not. So if it is yes, that is it is within the outcome of the set, that indicates 1. If it is outside, then it indicates 0. So this kind of random variable is known as the indicator random variable. Independence of random variable. This is another important concept to understand when we can say that the two random variables are independent. The two random variables R1 and R2 are independent if for all x1 x2 belongs to this real line, there exists that probability of R1 equals to x1 and probability of R2 less than x2 is equals to probability of R1 equals to x1 multiplied by probability of R2 equals to x2. Then if this condition is satisfied, we say that these two random variables are independent. Now there are other kinds of independence are also there, which is known as the mutually independent, and there are k-wise or the pairwise independent. Suppose that there are more than 2 random variables, which is the R1, R2, R3. We will say that these are mutually independent if the probability of this particular that is R1 equals to x1 and R2 equals to x2, R3 equals to x3, and all is equals to the multiplication of their individual probabilities. Then this can be told that these random variables R1, R2, R3 are mutually independent. Then there are k-wise independent random variables. Now out of this set, suppose there are n random variables are there, and in that out of that n random variables, it will said to be k-wise independent if all the subsets of the k variables are mutually independent. So obviously the k is less than n. So whatever the total number of random variables are there, if I now pick up randomly k random variables, and if it satisfies that the mutual independence among these k random variables, then we say those n random variables are k-wise independent. Now if this k becomes 2, then when this number of the variable reduced to 2 out of n, I take the 2. Then if the subsets are mutually independent, then this random variable is said to be pairwise independent. So what is happening? Out of n random variables, I am picking up in random, I am picking up only 2 random variables. One small correction here is that what that R2 is less than equals to x2 was written, so it should be R2 equals to x2. Now the most important thing why we just learn this random variable is that probability distribution of random variables. The distribution function of a random variable x is a function which is denoted by this capital letter F subscript the capital letter of that random variable. If it is x, then this is the capital letter of this x, with some smaller case letter. It may or may not be a x, which can take in any letter. So which is nothing but this inside this one, it is nothing but, as few previous slide we have seen, that this is nothing but the specific value of that random variable. So this is denoted as this is the distribution function of the random variable x, which is nothing but is the probability of that random variable x when it is less than equals to that specific value of that random variable. So, this is the way we define that distribution function of the random variable x, which is valid over the region from the minus infinity to the plus in infinity. So, the entire real axis. So, here again the general notation says that the distribution function of x, y and z are generally denoted by f subscript capital X, any letter lowercase letter fx x, fy y, fz z respectively. These variables, there is a lowercase letters, that what I was just telling here is x inside y inside z inside the parenthesis can be denoted by any letter, as these are nothing but the specific value of that random variable. This is also known as the cumulative distribution function, when in the most probably in the next class we will just discuss about this cumulative distribution function. This is actually the cumulative distribution function of this particular random variable. This will be discussed along with the probability density function PDF later. So, what we want to tell is that for a particular random variable, this random variable over this range, some probabilities are assigned for the specific range, and that the how it is distributed over this real axis is known as the distribution function of that particular random variable. Now, probability distribution of different types of random variables. Now, we have discussed about 3 different types of random variable. The first is the discrete random variable. We will see how it is defined, that it is a mathematical function denoted by, generally for when it is discrete we denote is by this px. This is also known as the probability mass function, we will discuss it later. So, this is denoted by px that satisfies the following properties. The first one is that the probability of any particular event x, because this is, as it is discrete, it can take any specific value, all means those specific value which is there in the feasible sample space. So, that particular specific value is denoted by px, which is nothing but the probability of the random variable taking the specific value x, denoted by either p inside that specific value x or p subscript that value in that specific value. Obviously, from the axioms of this probability, this px is non-negative for all real x. It can either 0 or greater than 0, and summation of this all this px over this possible values of x is 1. This is again from the axioms of this probability. Though mathematically there is no restriction, in practice discrete probability distribution functions only defines the integer values. So, this is just when we have also seen in previous slide that some example of this discrete probability distribution, that this is generally take the integer values, but it is not mathematically there is no restriction, it can take any specific value, the way I am defining that random variable. Second type of this random variable is a continuous random variable. So, this continuous distribution function for that thing, it is again a mathematical function which is denoted by this capital F subscript that random variable and any lowercase letter, particularly this random variable lowercase letter, that satisfy the following properties. The first is that for any specific value of this s, this should be greater than equal to 0. It is monotonically increasing and continuous function. So, here it is monotonically increasing, that means whenever it starts from, and it will go on in increasing, and you know that this can go maximum. So, generally for it is defined from the 0 to 1. So, this it can go up, it starts from 0 and go up to 1, and it increases monotonically, and it is an continuous function, as this random variable itself is continuous. So, it is 1 at x equals to infinity and 0 at x equals to minus infinity, that is this probability at this x is 1 and probability x minus infinity is 0. Then the last thing is this mixed probability distribution, which can take for some range it can take that discrete values and some ranges can take the continuous values. This is also denoted by Afx, and keeping the all other properties, all other conditions, that is the properties are same, which is obviously greater than equal to 0. The only difference with this continuous is that it is monotonically increasing function with certain jumps or the steps, and again the third one is again same. Now this one, this lies the difference between this continuous probability distribution and this mixed probability distribution. Now if we just see it here, as we are just telling that there are at some point where the probability is concentrated. Now if I want to just see that how it is accumulated over time, so it starts from here and it will go up to, maybe the way it is drawn, it should be asymptotic to 1. So this is the jump that we are talking about. So this jump where the probability masses are concentrated, here it is only 1, so it can be concentrated in some other range, then there also will be one jump. So wherever the probability mass is concentrated for some specific value, so there generally in this distribution function we see that type of jump here, which is the mixed probability distribution. Now the concept, the usage of this concept of this random variable in statistics, it is a never ending list, I should say. So here are just few examples are given. To calculate the intervals of the parameter and to calculate the critical region, we will see this what is critical region and this interval of parameters in the subsequent classes. To determine the reasonable distributional model for univariate data. Now this data can be of any field of the civil engineering. So now for this analysis, the distributional model for those kind of data, this is useful. To verify the distributional assumptions, so we generally for any probabilistic model we assume some distribution. Now we have to verify whether that particular distribution is followed or not. To study the simulation of random numbers generated from a specific probability distribution. Coming to the specific civil engineering, there are different facets of civil engineering, starting from water resource engineering, geotechnical engineering, structural engineering, transportation engineering, environmental engineering, and there are many such. So in water resource, for one example, the analysis of flood frequency, this concept is used. In geotechnical engineering, distribution of in situ stresses in the rock surrounding an opening, or the uniaxial compressive strength of the rock specimen, etc. In structural engineering, distribution of the damage stress in a masonry structure, etc., to check the seismic vulnerability of the structure. Transportation engineering, for example, the traffic volume analysis and this kind of thing in different application of this civil engineering. Now we will see the concept of the percentile for a random variable. The u percentile of a random variable x is the smallest number xu, so that u equals to the probability of x less than u, which is equals to the probability of xu. So to determine what is the value of this xu, the xu is generally the inverse of the distribution function fx, that is xu is equals to the fx inverse u within the domain 0 to u to 1. So now to know this thing, basically if the graphically, if I just want to see it here, now so this is the feasible range of that particular variable. So suppose this goes on here. So now to calculate this percentile, what some percentile, if we just say some u, so here we generally say where is the u. Now basically suppose this is here. So basically we just go and see how much percentage is covered here. So this particular value is the graphically representing, this particular value is your u percentile of that random variable. So generally what happens, we generally see this particular value, calculates its cumulative probability and get this one. So that is your, what is your mapping as this fx of any value x, that is your mapping. Now when we are coming from this side, then what we are doing, we are just giving this fx of u inverse will give you some value, that xu, which is your xu here. So, this is that inverse inverse function of that one to get that percentile. So, it's so the u percentile of a random variable x is the smallest number xu, so that u equals to probability of x less than equals to xu. So, this is obtained that xu is equals to inverse of that distribution of that particular number particular random variable for that percentile u. And obviously, the u have the range from 0 to 1, and so it is expressed in percentage is taken from this 0 to 1 range, and the range of x being whatever the range of that particular random variable. There are different properties of this distribution functions. So, we will see one by another, one by one of these properties, and in this discussion we will follow some notation. This is taken from mostly the Papule's book. So, this is that f of x plus of this random variable x, of course, is equals to limit f that particular value x plus epsilon, and f minus means the limit of this one when these epsilons are greater than 0, but it is tending to 0. So, very small number. So, this f x plus means just right side of that x, and f x minus is just left side of that x. So, property 1, the first property, that is, if I take this distribution function for this infinity is equals to 1. So, that right extreme of this real axis and the left extreme of the real axis, it starts from 0. So, it always starts from 0, ends at 1. So, to prove this one, that is f plus infinity is equals to f x less than equals to plus infinity. So, if it is f x less than equals to plus infinity, that means it is encompassing the full sample space. So, this is nothing but the probability of the full sample space S, and we know that this full sample space from the axioms of the probability that this is equals to 1. Similarly, so f minus infinity is nothing but the probability of x equals to x less than equals to, basically less than equals to minus infinity, which is basically null set. So, probability of the null set is equals to 0. Second property, f x is a non-decreasing function of x, that is, this non-decreasing function or monotonically increasing function, which is the word that we used a few slides previous. So, it says that if that x 1 is less than x 2, then always this f x 1, the value of this distribution function at x 1 is less than equals to f x 2. So, it can never decrease. So, it will always it will either be same or it will increase. So, and that is basically what is known as this monotonically increasing. Proof of this one is that if x j is less than equals to x 1 and x j is less than equals to x 2 for some outcome of this j, then x random variable less than equals to x 1 is a subset of the event x less than equals to x 2. So, what? So, this x 1 is always there within this x less than equals to x 2, if this is greater than if this x 1 is less than x 2. So, that is why if it is a subset of this one, then obviously the probability of this should be less than equals to probability of this x less than x 2. f x increases from 0 to 1, sorry for this mistake, f x increases from 0 to 1 as x increases from minus infinity to plus infinity. This will be 0 to 1 as x increases from minus infinity to plus infinity. Third property says that if x naught is equals to 0, then f x equals to 0 for any which is less than this x naught. So, for a specific value, if the f x equals to 0, anything which is lower than this x naught obviously will be 0. This is basically the same concept of that it is non decreasing function. So, if it is some portion, if it is 0, left side of that in the real axis context, that is lower than any value of this x naught, obviously that will also be 0. Proof says since f minus infinity equals to 0, suppose that x xi is greater than or equal to 0 for every xi, f 0 is equals to probability x less than equals to 0 is equals to 0, as x less than equals to 0 is an impossible event. So, f x is 0 for each x less than x naught, this is x naught. Property 4, if probability x greater than x is equals to 1 minus f x. So, probability x less than equals to f x is equals to f x, we designate in this way. Now, we know that total probability is always 1. So, if I just want to know what is the probability of x greater than x, obviously this is the rest of this probability. So, which is 1 minus f x. Proof says the event x less than equals to 1 and x greater than x are mutually exclusive. So, if these two events are mutually exclusive and collectively exhaustive, so collectively exhaustive means this x less than equals to x union x greater than x equals to the full sample space S. So, that probability of this less than x and greater than x is nothing but probability of the total sample space, that is the S equals to equal to 1, and now this is denoted by f x, which is this one equals to 1. So, probability of x greater than x equals to 1 minus f x. The fifth property says the function f x is continuous from right. So, f x plus, that is from the right, is equals to f x. Proof, since probability of x less than equals to x plus xi, where this xi is nothing but very is tending to 0, is equals to f x x plus xi, and f x plus xi is tending to f x plus when this x is less than equals to x xi is tending to f x less than equal to x, as this xi is tending to 0. So, that is why this is from this right hand side, if we say, then this is continuous from the right hand side of any specific value x. Then sixth property says for a random variable, if it is bounded by this x1 and x2, the probability of the value from starting from x1 to x2 is equals to the probability of x2 minus x01. So, graphically if I just see it again here, that is if I just take two values, if this is your say starts from 0 and goes like this. So, if I want to know that what if this is your x1 and this is x2, then this probabilities, that is x2. So, probability that f x less than equals to x2 is nothing but this particular value. Now, probability of x less than equals to x1 is nothing but this particular value. Now, if I want to know that if this x is in between these two, x2 and x1, then this probability is nothing but whatever the total probability this minus this probability. So, this is the probability that we are talking about, which is nothing but the probability of x1 less than equals to x less than equals to x2. Okay. So, this is how we get the probability for a range which are again this proof says that x less than equals to x1 and this x1 less than x2 are mutually exclusive, and again x less than equals to x2 is equals to x less than equals to x1 union x1 to x2, this range. So, the probability x less than equals to x2 is probability x less than equals to x1 plus probability x in between x1 to x2, or if I just take this one here, then probability of x1, this x random variable between x1 to x2 is equals to probability of x less than x2 minus probability of x1, which is again nothing but this f x1 f x2. Now, the property 7 says that if probability of x is equals to a particular value x is equals to probability of x minus probability of x just left to that that one. So, at a particular point the probability there. So, now these properties are in general for this discrete and continuous. So, for a particular point the probability says that it is at that particular point and just left to that whatever the probability is there. So, it will be like this from that particular side to just to the left of this one. Proof: putting that x1 equals to x minus j and x2 equals to x in this property 6, then we can say that probability of x minus j less than x less than that x equals to probability of x equals to probability x minus j. Now, taking this j tending to 0, then we can say that probability at a particular specific value is that point, probability at that point minus immediate previous value to that one, that particular value. So, if it is a discrete random variable, then just left to this value, this generally comes to 0. So, that for a discrete value at a particular point, the probability is equals to that particular the functional value at that particular point. Okay, finally, in this lecture we have seen that random variable is not a variable, rather a function which map all the feasible outcome of an experiment on the real line or a set of real numbers. A complex random variable can only be defined by the joint distribution of the real and the imaginary variable. That is, if that x plus I y will be equal to that the joint distribution of this x and y, both the random variables. Random variables can be either discrete or continuous if the set of events defined by this variable is either finite or infinite numbers respectively. Mixed distributions are the combination of both discrete and continuous distribution. Distribution of random variable with specific application to these different civil engineering related problems will be discussed in the next lecture, along with the concept of this probability density function and cumulative distribution function. Thank you.